In this video, we're going to continue our discussion of elementary matrices. We're going to see a few more examples. I encourage you to pause the video, try the examples on your own, and then come back and check your answers either with the video or with the calculator. Remember, the row operations I use may be slightly different than the row operations you use, and that's perfectly fine. So our elementary matrices may not be the same because of different row operations. However, the result should be the same. When we rewrite these matrices, you can always check it in your calculator. And then towards the end, we're going to talk about some equivalent conditions on matrices, and we're going to talk about square matrices in specific there. And then we're going to define what's called LU factorization, where we can factor a matrix into lower and upper triangular matrices. So lots of good stuff coming up. Let's continue with elementary matrices. And the next two problems, we want to find a sequence of elementary matrices whose product is the given non-singular matrix. So again, we're trying to rewrite A as a product of a whole bunch of elementary matrices. So let's try it. So there's 29. Our first step is to turn this into the identity matrix using row operations. Now, we know we're going to be able to do that because this is a non-singular matrix, which means it is invertible. So here's the way I'm going to do it. Here's what I see. I can replace row 1 with row 1 plus -1 times row 2. And that's going to give me a 1 in that top left-hand corner. So that's kind of a clever way to do this one to avoid fractions. Again, you may have chosen a different row operation. You may have said row 1 is equal to 1/4 row 1. That's perfectly fine. That just means your elementary matrix will look different than mine. Lots of different ways to get to that final answer. So now I'm going to take row 2 and replace it with row 2 plus -3 times row 1. And then I'm going to take row 3 and replace it with a -1 times row 3. Just kidding, that's row 2. And that's going to give me the identity for a 2 by 2. So now that I have that identity, and I've performed all these row operations, I can figure out what my elementary matrices are going to be. So E1 is going to look like that. E2 is that. And then E3 is that. Now, we've been using the result, really define the definition of row equivalence going way back to the beginning of this section series, where we said B could be rewritten as EK minus 1, just as multiplying all these elementary matrices together. So in this case, we ended up with the identity. That's going to be equal to E3 times E2 times E1 times A. So to undo this, remember the goal. The goal is to write A is equal to a product of elementary matrices. So we need to get A by itself. Well, to get A by itself, we can multiply by the inverse for each one of these. So we're going to have E3 inverse. Then we're going to have to multiply by E2 inverse. And then multiply by E1 inverse. And that will give us that A matrix. So there's the way we could write that. You can always check this in the calculator. Type in your elementary matrices and then compute that product to see if it gives it to you. This will work out. I've already checked everything. It's a good thing to double check on a test quiz or final exam especially. But if you use different row operations, it's a great way to double check your work. Let's do another one. Let's do that next one. This was number 32. So 3 by 3. So I need to turn this into the identity matrix since it's non-singular. So row 2 is going to be equal to row 2 plus negative 2 times row 1. And then I'm going to take row 3 and replace it with row 3 plus negative 1 times row 1. Notice row 1 staying the same. Yep. So row 2, 2 minus 2 is 0. 5 minus 4 is 1. 6 minus 6 is 0. 1 minus 1. 3 minus 2. 4 minus 3. So row 3 is row 3 plus negative 1 times row 2. So then row 1 is going to be row 1 plus negative 3 times row 3. And then row 1 is row 1 plus negative 2 times row 2. And that's going to give us the identity. So now let's find those elementary matrices. So E1 will perform that same operation on the identity for a 3 by 3. So it's going to replace row 2 with row 2 plus negative 2 times row 1. So there's our new row 2. E2 is going to come from replacing row 3 with row 3 plus negative 1 times row 1. E4, just kidding, E3. It's going to replace row 3 with row 3 plus negative 1 times row 2. E4 is replacing row 1 and then E5 replaces row 1 also. So the identity is row equivalent to A, which means I can write that identity as a series of elementary matrices multiplied by A. The goal is to get A by itself, to write A as a product of elementary matrices. So if we multiply on the left by E5 inverse, then E4 inverse, then E3 inverse, and so on, we will be able to achieve that goal. So there's our product. And I'm going to write those out. So if we were to write the inverse of E1, let's go ahead and go back here and do that. What would the inverse of this guy look like? I'm going to do that in a different color. Well, that inverse would undo that 2 here. So it would have to have a positive 2 there. What about the inverse for E2? It would have to undo that negative 1 there. So it would look like this. What about E3 inverse? It's going to have to undo what's going on with that bottom down here. So it would have to look like this. And then E4 inverse has to undo that negative 3. And then E5 inverse has to undo the negative 2 on the top. So you're always thinking about what row operation would have to be performed to get this back to the identity. So now that we've defined what each of those are, then this answer would be fine. So if this were a test quiz or final exam question, I would expect you to be able to tell me what each of those are. You don't have to write all 5 of those matrices again, as long as you identify them somewhere. I don't believe we did that up here. Let's go ahead and go back and identify what those inverses would look like for that previous problem. So if we look at this one, E1 inverse would undo this row operation. So it would replace row 1 with row 1 plus 1 times row 2, which would have that inverse. E2 inverse would undo this row operation. So it would be row 2 is equal to row 2 plus 3 times row 1. And then E3 inverse would undo this row operation. So it would be row 2 is equal to negative 1 times row 2. So this one will end up being the inverse of itself. And now that we've defined what the elementary matrices look like and what the inverse matrices look like, then it would be perfectly fine to leave your answer this way. Especially if this were a test quiz or final exam question. So we're building this set of equivalent conditions. So if we look at theorem 2.15, if A is an n by n matrix, that means it has to be a square matrix, then the following statements are equivalent. So if A is invertible, then that's the same thing as saying that AX equals B has a unique solution. That also means that if we replace that B with 0, so that this is a homogeneous set of equations, then that means that because there has to be one unique solution, then the only solution would be the trivial solution. And remember, the trivial solution is when x is equal to 0, y is equal to 0, and z is equal to 0, if it were in 3 dimensions. Now, all of this is equivalent to saying that A is going to be row equivalent to I sub n. Remember, that's the identity for an order n matrix. So like a 2 by 2, it would be I2, 3 by 3 would be I3, and so on. What that means is that if A is invertible, if all of these hold, this has to be true. And that last one, number 4, says that we could take A, we can produce row operations, and we will eventually get to the identity matrix, which would be the RREF version of A. And if we can do all of that, then that guarantees 5 happens, which means that we could take that matrix A and we can write it as a product of elementary matrices. So all of these 5 criteria really are interchangeable with one another. If one happens, then that means that all 5 of those have to be true. So that's kind of a cool thing. And we'll keep building this list as we go through the course. So it's neat to see how everything's tying together. The last thing in this section is LU factorization. So we could take a matrix and we can factor it into a lower and an upper triangular matrix. So L is going to be a lower triangular. And what that means, if we have a lower triangular matrix, is that we're going to have entries down that main diagonal. So I'm just going to use X's here. We can have stuff down here. There could be zeros. There could be numbers. But what will always happen with a lower triangular matrix is that everything that is above that main diagonal will be zeros. So everything that's non-zero would be on the lower end. U is an upper triangular matrix. And what that means is that we have this matrix, and I'm just using 3x3s. We're going to have stuff down that main diagonal, but all of your numbers, non-zero numbers, would have to be above that main diagonal, because everything below, to be an upper triangular matrix, everything below that main diagonal has to be a 0. So if we have an n by n matrix, and it can be written as a product of, a lower triangular matrix and an upper triangular matrix. And that LU decomposition is called LU factorization. So we can kind of factor it into a lower and upper triangular matrix. So let's look at a few examples. So our first step is to do row operations until we get to an upper triangular matrix. We don't have to necessarily go to REF or RREF. We just want to get to an upper triangular matrix. So I'm going to take row 1 here, and I'm going to replace it with negative row 1. I'm going to try to do this without fractions. So we're going to have a 2, a negative 1 here, negative 6 and 4 here. And then I'm going to replace row 2 with row 2 plus 3 times row 1. So this is an upper triangular matrix. I'm going to call that U. Now, it took me 2 row operations to get here. So my E1 is going to come from that first row operation. And my E2 is going to come from that second one. So right now, what we're saying is that this matrix U is row equivalent to this matrix. So going back to that definition of row equivalency that we talked about on the first page of the notes, we're saying 2, negative 1, 0, 1 is going to be equal to E2 times E1 times that matrix we started with. I'm going to call it matrix A, which is negative 2, 1, negative 6, 4. And this is U. So our goal is to decompose. So we're kind of on our way, but remember, we want to write A as a product of L times U. Well, let's get A by itself. So if I get A by itself, right now, here's what I have. To get A by itself, I'm going to multiply by E2 inverse on the left, And then I'm going to multiply by E1 inverse on the left. So E1 was negative 1, 0, 0, 1. E2 was 1, 0, 3, 1. I need to take the inverse of each one of those. That's going to give me my L. Well, the inverse of that first one will be negative 1, 0, 0, 1. The inverse of the second one is an elementary matrix, so it would be 1, 0, negative 3, 1. So this first matrix, notice that we just have entries down that main diagonal. That's actually called a diagonal matrix. That second one is a lower matrix. So if I take a diagonal times a lower matrix, I'm going to get a diagonal matrix or a lower matrix. In this case, it will be a lower. So we're going to have negative 1 times 0, 0 times 0 plus 0, 0 minus 3, and then 0 plus 1. So there's our lower matrix. Our upper one we said was 2, negative 1, 0, 1. So there's our upper. Just kidding. There's our lower, there's our upper. And that's got to be equal to what we started with. So this is an LU decomposition or factorization of this matrix. Now, this is not unique. You could have chosen different row operations. So think about what we're doing, what your goal is. So let's write out some steps. So your first step is to use row operations to get A to an upper triangular matrix. So then you want to rewrite, after you do that, that upper triangular matrix in terms of a product of elementary matrices times matrix A. So then A is going to be equivalent to E1 inverse, E2 inverse, down to EK inverse times U. And this guy should end up being a U. Should end up being a lower triangular matrix when you multiply it together. So there are your steps. Let's do one more. So with 43, we're looking at this matrix. Remember the goal. Let's get it to an upper triangular matrix. We don't have to have ones down the main diagonal. You can if you want to. I'm not going to worry about that. It does not have to be an REF. It just has to be an upper triangular matrix. So I'm going to take row 2 and replace it with row 2 plus negative 2 row 1. I'm going to take row 3 and replace with row 3 plus row 1. So there's 2 row operations. And then I'm going to replace row 3 with row 3 plus negative 1 times row 1. Just kidding, row 2. So notice this guy is an upper triangular matrix. I'll say this is equal to my U. Now let's identify our E's. So E1, our first elementary matrix, is this. E2 is this. And then E3 is that. So U can be written as E3 times E2 times E1 times matrix A, which means A is equal to E1 inverse times E2 inverse times E3 inverse times U. So E1 inverse is this matrix. E1 inverse. E2 inverse is this one. E3 inverse is this one. U is this. And A is what we started with. So notice it took us 3 steps to get to an upper triangular matrix. The 3 steps we used produced 3 lower triangular matrices. That's going to be our L when we multiply them together. So when I multiply those together, I'm going to get this. So here is my LU decomposition. And we could always double check it, type it in the calculator, and you'll see that this is definitely going to work. So why on earth would we want to do something with LU factorization? Well, one thing that's nice is that we can actually solve a system of linear equations using LU factorization. If you're thinking about this, now keep in mind, we're in class, we're solving small systems. 2 by 2, 2 equations, 2 unknowns, 3 equations, 3 unknowns. Maybe if we get adventurous, 4 or 5 equations and 4 or 5 unknowns. And we're doing those by hand using Gaussian elimination. In the real world, you're going to have many more than 2 or 3 variables. You may have 15 or 20 variables. And your numbers may not be nice. They may be fractions. Well, what happens when you're programming something like that in a program like MATLAB, is that your calculations can get rounded. So the more steps you use, the more rounding error you're going to have. So LU decomposition will take out some of that rounding error for you. So here's how this works. So once we have an LU factorization, then we can solve the linear equations by creating, really breaking this down into 2 steps. We're going to let y equals u times x, and we're going to solve ly is equal to b for y. So I want you to think about y kind of like a dummy variable, if you will. And then that's going to allow us to substitute in so that we can use a back substitution method to get that final answer. So let's look at an example of how this is going to work. And remember, we're doing this with real small matrices. We're just going to use 3 equations, 3 unknowns. So we got to find the LU factorization. And then we're going to solve the system using the LU factorization so you can kind of see how this works firsthand. So our system is 2x plus y is equal to 1. Y minus z is equal to 2. Negative 2x plus y plus z is equal to negative 2. So our ax equals b looks like this. So let's take matrix A and let's break it down into a lower and upper triangular matrix. So I'm going to do row operations. So I'm going to take row 3 and replace it with row 3 plus row 1. And then I'm going to take row 3 again and replace it with row 3 plus negative 2 times row 2. And that's going to give me an upper triangular matrix. Remember, this is not the only way to do it. This is what I saw. So there's my U. We've done 2 row operations to get to an upper. So our E1 matrix is that. And our E2 comes from that second row operation. And it's that. So right now we have U is equal to E2 times E1 times A. So that means this is an equivalent statement. So our E1 inverse is that. Our E2 inverse is that. Notice those are both lower triangular matrices. Our U is this. And this is equal to A, which is what we started with. So that's going to be L when we multiply together. This guy's U, and this guy's A. Now if we were to multiply these together, we get that. So there's our decomposition. So that's your first step. Find your decomposition. Now I'm going to box this off so we don't lose it. So remember, we had AX is equal to B, right? But A is now replaced by L times U because that's equivalent to A. So what we're saying is we're going to let this be a dummy variable Y. So we have L, and our L is 1, 0, 0, 0, 1, 0, negative 1, 2, 1. Y is a dummy variable. I'm going to call it Y1, Y2, Y3. And I call it a dummy variable because it's something we introduce to, it's like a means to an end, to get us to the end. And our B was 1, 2, negative 2. So if we were to multiply L times Y here, we're going to get Y1 plus 0, which is Y1. So Y1 has to be equal to 1. We're going to have Y2 is equal to 2. And then we're going to have negative Y1 plus 2Y2 plus Y3 is equal to negative 2. So we know what Y1 and Y2 are. Let's solve for Y3. So Y3 is equal to Y1 minus 2Y2 minus 2. And if we make our substitution, then Y3 is equal to 1 minus 2 times 2 minus 2. So we're going to get negative 5. So that's nice. But now we need to solve that other equation in here. Ux equals y. So then we're going to solve that. So U was our matrix 2, 1, 0, 0, 1, negative 1, 0, 0, 3. And we're looking for x. I believe we used XYZ in the original problem just to not get it confused with this y that was a dummy variable down here. I'm just going to call it x1, x2, x3. That has to be equal to y, and our y was 1, 2, negative 5. So let's multiply through. Now we have an upper triangular matrix times this variable vector. And we'll be able to do some back substitution, kind of like what we did here to solve for the y's. So we have 2x1 plus x2 has to be equal to 1. We have x2 minus x3 has to be equal to negative 5. Only right underneath. And that's equal to a 2. So x2 minus x3 is equal to a 2. And then we have x3 is equal to a negative 5. So that's what that system is saying. Well, if we know that 3x3 is equal to a negative 5, then that means that x3 has to be equal to negative 5 over 3. So we know what x3 is. And since we know x3, then we can find x2. So if I do a substitution there, x2 is going to be equal to x3 plus 2. And then if I sub in, then x2 is going to be equal to negative 5/3 plus 2. And that's going to be equal to 1/3. And then So now we have x3 and x2. Now we got to find x1. And that's going to come from here. So we're going to do a substitution. So x1 is going to be equal to 1 minus x2 divided by 2. X2 is 1/3. And that's going to be equal to 1/3 also. So then x1 is equal to 1/3, x2 is equal to 1/3, and x3 is equal to negative 5/3. So there's our solution to this guy. And that's using that LU decomposition. Now notice we didn't have to deal with any fractions until we got to the very end. So imagine if we were programming something in the calculator. Maybe we had a bigger system. Maybe we had 20 unknowns, which means we have to have 20 equations. And we were dealing with fractions like 1/3. And if we had to round those, and MATLAB will round, I don't think it rounds until like the 20th decimal place. But if you're rounding over and over and over and over and over, imagine the rounding issues that can present themselves. And you're looking as an engineer for an exact solution. So you can see how this would be a little bit better to program than something that's going to round and cause some major issues with rounding issues. So there's our final solution.